All right, welcome everybody. So today we're going to be talking about two more quizzes. The first quiz is going to be on some quantum stuff. It's going to be on the photoelectric effect, and particularly the photoelectric effect in the context of the quantum harmonic oscillator, whose energy levels are defined by this. The other one is an optics problem. So this is going to be a problem for having to do with mirrors. So cool, it's a mirror problem, a single mirror. Okay, so let's just begin at the beginning. We'll start with the quantum quiz. Now, there's two key, well, yeah, okay, fine. There's two key intuitions to take away from quantum, I think. The first is that matter actually exists as essentially like standing waves of probability. So instead of things having very specific locations, they have these kind of like gooey locations that are spread out. So when you look at like the standing wave of the, when you look at the standing wave of a particle in a box, so departing a little bit from the problem here, if I look at a standing wave like this is a probability wave. So an infinite 1D particle in a box, boom, length L. This is a probability wave, or it is if I square it, whatever. It's basically a probability wave. The regions where it's most likely to be are regions like this, where we've got a lot of, like the function is relatively large, far from zero. And the regions where it's not likely to be are regions like over here, where the function is near zero. So that's the first intuition. The other cool intuition from quantum physics is that light comes in quantized packets. Light comes in quantized packets. So what that means is that there are photons exist. There you go. And photons carry energy in chunks. Let's say it like that. And we get into a little bit more detail there, but for now, I'll just leave it there. So yeah, like an individual photon of a given wavelength has a corresponding amount of energy. Okay, on to the problem, is that all right? But that's kind of the two main intuitions we want to take away from quantum mechanics in here. So this first question asks, using some clever techniques, well, let's read the intro first. Using some clever techniques that are sadly beyond the scope of this course, it can be shown that the energy levels of a quantum harmonic oscillator, for example, a vibrating chemical bond, obeys a very simple equation. En equals some constant E times n, an index, plus a half. So to draw this on like an energy axis, E, this is one that starts off at, let's see, that'll be E n plus 1/2, so this will be E over 2. The next one will be 3E over 2. Then 5E over 2, and so on. They're linearly spaced out, these energies, 7E over 2. It's not necessary to draw this diagram for this problem necessarily. I'm just kind of trying to indicate how the energies look for this quantum harmonic oscillator. It's equally spaced between energy levels. So this is the n equals 0 line, n equals 1 line, n equals 2 line, and so on. Okay, for the case, let's go down, where En is the energy of the nth state and E is some material specific constant. Note that the ground state corresponds to n equals 0. Nice, good hint. So the ground state is n equals 0. Good piece of vocab to have. This is true for the quantum harmonic oscillator only. I think the rest of them start at n equals 1. Yeah, I think that's right. For the case of the vibrations of molecular nitrogen, that constant E is 5.5 times 10 to the negative 20th joules. They ask us, what is the wavelength of the photon emitted when a nitrogen molecule decays from its first excited state to its ground state? So what we're really talking about here is like a molecule of nitrogen that has some energy in it. It's somehow excited up to its first excited state. It's at the n equals 1 state. And broadly, this is not a general rule, but just in like broad strokes, I usually think of this as meaning like the particle is a little bit more excited and spread out, right? So if you think about the hydrogen atom, if you think about orbitals that are farther away, you'd expect them to have higher energy than orbitals that are closer, right? So intuitively, this is kind of the way that I think about it. It's like I'm going from something that's more spread out, kind of like a pulled apart spring, to something that's less, that's a little bit more contained, a little bit less energetic. That's an intuition that I have. That's not like required for you to do the problem. That's just the way that I think about it. Okay, but so functionally, all we need to do is figure out the energy. So this is the n equals 2 state, and let's say it decays to the n equals 1 state. It's going to emit a photon. So we want to figure out the wavelength associated with that photon. Now, where does that photon get its energy? This is what's called the photoelectric effect. The photoelectric effect is the idea that when a quantum system changes states, it can emit a photon. So that energy has to go somewhere from changing states. And if it changes states from 2 to 1, that represents a drop in energy. So we emit that energy as a photon. If we were to go from n equals 1 to n equals 5, well, that would mean that we were going up in energy. So we need to absorb a photon. A photon would have to have hit us to cause that energy level change. Questions there? Because that's really like the meat of this problem. And then the rest of it's just calculation. Can I get some thumbs? Let me get thumbs up if you're like all right, and then open mouth if you're like ah. Okay, fair. Some no responses. That's all right. That's all right. I could use an app for me. Oh, I have a raised hand, or maybe that's just a missed thumb.
Yeah, no, I had a quick question. So what was this like little diagram that you drew like supposed to represent again from the question?
The one on the far left, or this one here?
The circles, yeah, the second one.
Yeah, sure. So this is the intuition that I have about what this physical transition corresponds to. So basically what I'm trying to say is that there are being in an excited state, so being above the ground level, means something like particles are spaced farther apart. In the context of the hydrogen atom, it usually means that the electron cloud like gets bigger, right? So if you think about the 2s cloud, 1s, 2s. Gross. All right, well, I'm not going to get that. Fine. they're increasing, they're orbs of increasing radius. So this is getting a little bit like outside the scope of the course, I'd say, but just the way that I think about it is the higher my energy level, the higher my energy of a quantum system, kind of the more spread out its wave function will be, the more spread out it will look. Is that okay for now? So when I try to draw this little picture, I'm visualizing my system, which is like in a more spread out state, a larger energy state, and it's condensing, it's losing energy and dropping to a smaller energy state. As a result, it spits out a photon, which is what this squiggle is supposed to represent, photon. Is that okay?
Yeah, that makes more sense. Thank you.
Nice. Okay, good stuff. Yeah. I drew a random squiggle, right? Random squiggle, what does that mean? Yeah. Okay. So we're going from the n equals 2 to the n equals, from the first excited state, that's the n equals 1 state, to the ground state. We'll go and write that in just so we're clear. N equals 1 to the ground state, n equals 0. So here we go. What this tells me, the basic idea of the photoelectric effect is that the energy of a photon is equal to the energy of a photon emitted or absorbed by a quantum system is equal to the change of energy, of the quantum system. What does that mean? In this case, the photon energy is E1 minus E0, where the subscript.
Shouldn't it be E0 minus E1?
So right.
With 0.
So you're right. It should actually be negative here. You got me. Or maybe it's better to even just call it magnitude. So final minus initial will tell me the change in energy of the quantum system. What I actually want is the opposite of that, because the change in energy of the quantum system, yeah, we should throw a negative on here. That'll make the most sense. The change in energy of the quantum system is the thing that fuels the photon. Does that kind of make sense? So I'm not looking for the change in energy of the quantum system. I'm looking for the opposite of the change. In other words, I'm trying to figure out
So instead of doing negative delta, could we also just do E0 minus E1?
Yes, that's equivalent. Yep. That's
Okay,
equivalent.
yeah.
So if you do E naught minus E1, you'll find a negative energy, which doesn't make physical
Yeah.
sense. Photons
I
have to have
guess like,
positive energies.
oh, okay.
Yeah, but the magnitude will be the same regardless. Yeah, so as long as you're comfortable taking the absolute value, and just like knowing that photons can't have negative energies, we're not going to dock points for that.
Oh, because I thought if it has a negative in front of the energy, it just means that it's being released.
That's not true in general. No, the negative in front doesn't necessarily mean that energy is being released.
Okay. Okay.
I guess. Oh, you're okay. I think I see what you're saying. So if the delta E, so if hang on, let me erase. If just this is negative, if
Yeah.
delta quantum system is negative, that does mean that energy is being released by the system.
Okay.
Yeah. Yep. Sorry, I thought you meant this whole thing, including the negative sign. You mean the opposite then.
Oh, yeah, yeah.
But good, that's good intuition. If the change in energy of the quantum system is negative, then energy is being released. If the change is positive, energy is being absorbed. I got another question. Can you repeat the photoelectric effect part? So the key intuition of the photoelectric effect is that energy changes in quantum systems, as far as we know, as in here, energy changes in quantum systems are driven by changes are driven by the production or absorption of photons, which are like light particles. So the idea is that a quantum system reduces its energy and emits some light in the form of this single particle, this photon. Or alternatively, a quantum system increases its energy by absorbing a photon that wiggles its way in. Okay, so let's find that energy. Let's find that energy. E1 minus E0. E1 is going to be what? E1 is just E times 1 plus 1/2 minus E0, which is E times 0 plus 1/2. Okay, great, which is just 3/2 E minus 1/2 E, or 1E. Notice that E here, this E, doesn't have a subscript. It's just this constant. So we're not talking about like a function. We're not talking about E photon. We're just talking about this constant E that they provided to us, which is the same as 5.5 times 10 to the negative 20th joules. All right, what was the point of that? Why did I find that energy? Well, the good news about photons is if we know a photon energy, we have a relationship that can take us directly to wavelength. So if I check out down here, the energy of a photon is HF, where H is Planck's
Wait,
constant.
isn't it energy equals to HF over wavelength? Because like if you go down to the formula below, I think you forgot to box the wavelength part.
So it's not about.
Yeah, because like there's 1 over wavelength on the right side. Because it should be energy equals to HF times 1 divided by wavelength.
So it's actually this is good. This is a good clarifying point. It's actually not HF divided by wavelength. It's HC divided by wavelength.
Oh, sorry. Okay.
You're good. So this part here, F being equal to C over lambda, is just something we've already seen before, which is V equals lambda F rearranged. So F is V over lambda. And for light particles, or for light, like a photon, V is just C, the speed of light. Okay, so, but this is kind of a two-parter here. We have E equals HF. That gives us this relationship, E equals HC over lambda. Solving that one back, we get lambda equals HC over E, photon. And I should make this explicit. This is also photon energy. Okay, so I'm going to solve back for that. But first, a quick broad strokes. How do we approach this problem? Step 1, identify that it's the photoelectric effect. So I noticed that there's both talk of a photon, light waves, and talk of a quantum system. Probably going to be a photoelectric effect problem. Next thing I did was I assembled 2 equations. The first is just a statement of the photoelectric effect, that the energy of a photon is the opposite of the change in energy of my quantum system. The second is by manipulating this relationship. Energy of a photon is hf, the frequency of that photon. H is just Planck's constant, it's a very small number. That reduces to hc over lambda if I make a substitution for f, frequency. All right, now I've got that. I also know the energy of my photon, 5.5 times 10 to the negative 20th joules. So now we're pretty much ready to go. The wavelength is hc, which is, oh goodness, blah, 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 blah. H is 6.26 times 10 to the negative 34th. Here we go. 6.626 times 10 to the negative 34th times 3 times 10 to the 8th. And this will be all in SI units. So what will come out will be in terms of meters. And this one, the energy of a photon, 5.5 times 10 to the negative 20th joules. Whew. All right, I'll race you. Who can do the calculation fastest? Okay, I get 3.61 times 10 to the negative 6th meters, which is 361. Wait a minute. Wow, that's really long, actually. Feels a little longer than I would guess, but that would be 3,600 nanometers. 3,614 nanometers. That's my wavelength.
Wait, so it's 1 meter 10 to the 9th nanometers?
That's right. That's sorry, other way around. So
sorry.
Sure. 1 nanometer is 1 times 10 to the negative 9th meters.
Okay.
But if you said, is a nanometer the same as 10 to the 9th, or is a meter the same as 10 to the 9th nanometers, that's also correct. Yeah. On the left side here, I know my handwriting is kind of sloppy. This is nanometers. You can, but you have to convert J to EV. I'm pretty sure you can. Why can't we use 1240 for H? That's right. Yep. Okay, good question. So why can't we use 1240 for HC? The reason I didn't choose to use 1240 for HC is because the energy that I have for my photon energy is in units of joules. So 1240 for HC is 1240 EV times nanometers. So EV is a different unit of energy than joules. So that's why I stuck with joules the whole way through. Awesome. Okay, thanks, chat. Let's go ahead and move down to part B. What wavelength photon must a nitrogen molecule absorb to go from its n equals 4 to n equals 5 excited state? Okay, this is just a repeat, essentially, right? We're doing the same process. We're doing the same thing again. So I'm going to do it fast, and then see if you can keep up. I'm gonna ask y'all for the wavelength at the end. Ready? Okay. So we have E equals hc over lambda. We have delta E system equals E photon. And as we said before, negative sign, delta E system. Hello, handwriting. All right, so let's go ahead and combine these. We're going to find the wavelength required. So lambda, I'm just going to solve for it algebraically. Lambda is hc over E photon. E photon is just negative delta E of the system. Negative, let's see, it's going to be E5 minus E4, final minus initial. Cool. Is that going to give me, I think I might end up with a negative number for wavelength here, but if I do, I just know to switch the sign, right? All good. So let's just do it in terms of joules again. So 6.626 times 10 to the negative 34th times 3 times 10 to the 8th over negative E5 minus E4. What's E5? Well, E5 is going to be E5 plus a half. So that's going to be, what's 5 plus a half? That's going to be 11 halves. Oh God. Yep, we're good. 11 halves E minus, and then E4. So that's going to be 9 halves E. That E is just 5.5 times 10 to the negative 20th. I'll go ahead and plug that in. (5.5 times 10 to the negative 20th), and solve back. So I'll go ahead and just say, I know the answer already. Do you know how?
Isn't it because 11 over 2 minus 9 over 2 is just 2 over 2, so it's just the same thing pretty much.
It's the same thing. That's right, exactly. It's the same thing. So because these energy levels of the harmonic oscillator are linearly spaced, I know the distance between any two energy levels. And then if I want, I can just, this distance, this energy difference between 0 and 1 is the same as the energy difference between 4 and 5, and so on, because those energy levels are linearly spaced. So this is one of those kinds of, this is one of those questions where there's a long way and there's a short way. The short way is just to say, because the energy levels are linearly spaced with n, the n equals 4 to n equals 5 excited state is the same energy, the same amount of energy as the n equals 0 to n equals 1 state. So that's going to end up being just, 3614 nanometers once again. I think I have chats coming in. Is it energy that is absorbed by nitrogen? Why delta E negative? Oh, I see. Yeah, so yeah, you're right. This really is better to, I'll change my notation on you. Regardless, so the physical intuition should always kick in and say that, how do you say it? The physical intuition should always kick in and say, hey, wait a minute, wavelengths can't be negative. But yeah, it really should be, I guess, the absolute value of the change in energy. That'll always get you the right answer. Yeah, as far as the energy of the photon, that's right. Yep, because photon energy always has to be positive, so there's no way this is ever going to steer you wrong. And in that case, we can just do absolute value, etc. For these problems, it should never really matter too much, that sign. You'll just see, okay, we would have popped out negative 3614 nanometers, and that obviously doesn't make sense. So it's got to be the positive one. Okay, hopefully that's okay for A and B. Any other quick questions? Otherwise, I'll chunk it down. Go for it.
I had a clarifying question.
Of course.
So, so for part B, we found out that the wavelength is the same as part A. So just to make sure I'm understanding this correctly, we would know that it's going to be the same wavelength due to each level being evenly spaced out.
Right. Every level is equally spaced out from the next adjacent level. Yep.
Okay. Thank you.
Yeah, good stuff. Thanks. And I can kind of see that visually from this equation. So since the energy is linear, I should zoom in. Since the energy is linear with n, like it's not n squared or 1 over n or anything like this, it's just n, the energy levels are going to be linearly spaced. I have another related question, which is it always the case that the energy levels are linearly spaced? And the answer to that is a definitive no. So of the quantum systems we've looked at, the only one that is linearly spaced is this quantum harmonic oscillator. That's it. The infinite potential well, or the particle in a box, the same thing. Same thing. Okay. So the particle in a box goes like n squared, so it's not linear. And the hydrogen atom goes like 1 over n, which is also not linear. Thanks for the question. Okay, we're rounding up on the halfway point. Seems about right. Seems about right. Let's go ahead and knock this one out. Sound good? Can I get some reactions again? How y'all feeling? Can we get thumbs up if you're all right? Open face if you're like, ah. That is still a reaction, right? Open mouth. Yeah, that's what I'm looking for. All right, varying amounts, varying amounts. Check out the chat. Thought I saw one more. Quick question. We have one more question coming in. I have a quick question. How do we know when to use the formula E equals h squared n squared over times, okay, ml squared versus the one that is negative 13.6 z squared over n squared? Interesting. Oh, okay, great. Okay, so Sharon asks basically which corresponds to which system. Let me post this for everyone. So the question is basically, when do we use those two energies? And I'll try to post them over in the Zyboard as well for people in the future. There we go. So
Is that one just for hydrogen?
that's right. The one on the right is for the hydrogen atom, or for hydrogen-like atoms, where Z is the number of protons. The one on the left is for the, I think it's an 8 here. The one on the left is for the particle in a box, 1D particle in a box. So there are 3 quantum systems we've studied. There's the particle in a box, there's the hydrogen atom, and there's the quantum harmonic oscillator. And those are our big 3. One more question coming in, which is for quantum harmonic oscillators, the different E's are equal at any level, right? The difference in energy is equal at any level, that's right. So the difference in energy is equal at any level between any adjacent levels. So these 2 levels have equal energy difference to these 2 energy levels, So all of these energy differences, these little deltas, those are all the same. Sharon asks, we would explicitly be told the scenario in a question, right? So that's a good question. It should be definitely obvious. So like the 1D particle in a box is its own one special theoretical thing. So yes, like 1D particle in a box, definitely. We may ask like general questions about quantum that are, you know, not super specific to like a hydrogen-like atom. But I'd say overall, yes, in anything where we're asking you to do any serious calculation, we'll tell you what kind of system it is, that's for sure. Another question for the H-like atom, how can Z be greater than 1 if we were only considering the hydrogen with 1 proton? Good. So a hydrogen-like atom is, for our purposes, is an atom which has 1 electron and just some number of protons. So you can imagine, for example, like a helium atom with 2 protons and 1 electron whizzing around out here somewhere. I won't draw that. So if we had a helium atom with only 1 electron, that would be like a hydrogen-like atom with Z equals 2. Hopefully that helps.
So is Z equal to the number of protons?
That's right. Z is the number of protons.
Okay. So
The number of
then,
protons in the nucleus.
okay, so then you couldn't use that equation, right? Because Z is not equal to 1.
So you can still use the equation. Oops, sorry. Z doesn't have to be equal to 1. Z can be, I mean, for the theory, it can be just any positive number, any positive integer. In practice,
Okay.
it only works super well for low Z. Yeah.
Okay.
But Z, for our purposes, the key thing to remember is just that Z is the number of protons in the nucleus of a hydrogen-like atom. Hydrogen-like here just means 1 electron, 1 electron. If you throw other electrons, as a point of trivia, this is not on the test, but if you throw other electrons in here, it just means that it just makes the electron kind of wig out. It starts to behave differently. So the orbitals, the electron clouds become different when you throw other electrons in there. All right, let's leave it alone for now. They start to interact with each other is another way to say that. Okay, part C, and then I'll stop boring the people who already love quantum and we'll move over to something a little more mirror-y. In 7a, you learned about mode freeze out. It turns out that freeze out happens when thermal energy, which if you remember the equipartition theorem, is 1/2 kBt for each mode. Remember modes? What a time it was. Okay, is small relative to the spacing between successive energy levels if there isn't enough thermal energy to move to higher energy levels. Based on this, do you expect the vibrational modes of N2 to be frozen out at room temperature? Recall KB equals 1.38 times 10 to the negative 23 joules per Kelvin. Okay, this is kind of interesting. So the way I interpret this one is that, so as a reminder, when we have vibrational modes for like N2, there's like translational modes, left, right, up, down, forward, back. There's rotational modes, spinning in 2 directions. And those are just kind of unlocked all the time, or at least, yeah, all right, those are kind of unlocked all the time. However, the vibrational mode, like jumping from the n equals 0 of vibration to the n equals 1. So n equals 0 would just be stationary, not moving. N equals 1 would be jiggling around a bunch, something like this. That corresponds to a quantum jump in energy. It's like a quantum harmonic oscillator, a quantum spring, right? These 2 atoms connected by a spring. So what I'm going to do is I want to compare the spacing between energy levels, compare the spacing between energy levels for N2 with the energy per mode at T equals 300. Okay, so the energy per mode at T equals 300 is kind of like how much energy could be allocated to vibrating. How much energy could be allocated to vibrating. The energy level, the spacing between energy levels for N2 is how much energy it would take for my N2 to start vibrating, for those vibrational modes to be active. So if delta E 1 to 0 is greater than 1/2 kBt, the energy per mode, then no vibration. No vibe modes.
Wait, why is it 1 to 0 for delta E?
So I just picked 1 to 0 arbitrarily, but basically it's any individual, like,
Oh, okay.
one particle
Is it
space.
because like if when you go 1 over for an energy level is the same for all of them?
That's right. That's right.
Okay.
Yep. That's right. That's why I can pick any 2 that are adjacent to one another. I could also pick like 3 and 2, but in my head, the reason that I picked 1 and 0, keeping it kind of low, is because when the energy is low, we're near the ground state, which would correspond to like not vibrating very much.
Isn't it possible to also go from 0 to 1 instead of 1 to 0?
Sure. I picked 1 to 0 because it keeps our sign positive, and there was a little bit about that. But yes, the magnitude will be the same, 0 to 1 or 1 to 0. Okay, and I'll put a magnitude sign just to be clear. If it's the other way, so if delta E is less than 1/2 kBt, then we have enough energy, we have enough thermal energy to excite those vibrational modes. So unfrozen, yay. Okay, so let's go ahead and calculate this number, 1/2 kBt. What's 1/2 kBt? At 300 Kelvin. So 1/2 kBt is going to be 1/2 times, what's kb here? Oh God, did I forget it? No, we're good. Okay, I didn't need to remember it. 1.38 times 10 to the negative 23rd joules per Kelvin times 300 Kelvin. That's 30. There's 300. Whoa, what is that number? (10 to the negative 23rd times 300). That's going to be, I get at least 2.07 times 10 to the negative 21 joules. Okay, so how much energy is associated with jumping between 2 energy levels? 5.5 times 10 to the negative 20th joules. Okay, cool. So what do we see? We see that the energy associated with the change is 5.5 times 10 to the negative 21 joules, or 20, sorry, 10 to the negative 20 joules. That's a big difference. So this number, the change in energy required to kind of unfreeze the nodes, is the mode is greater than the energy we actually have. It's about, what is that, like 20 times greater. So we find that delta E, 1 to 0, magnitude-wise, is greater than 1/2 kBt. So it's frozen. Okay, I know that this was probably the example. I think this is probably the furthest removed from DL, or DL might have touched something like this briefly, but only for a moment. So again, broad strokes for C. So for C here, what we did was we said, all right, what is the, here we go. What is the relative size of the available thermal energy per mode, 1/2 kBt, compared with the energy required to jump up an energy level? Kind of like the thing that wants to take that energy. If we have a lot of energy, like if we have a lot of energy to spare from our thermal fuel, then those modes are unlocked. If we don't have that much energy, those modes are not unlocked. We compared those two numbers, and it looked like that it's going to be frozen for us. We did not have enough thermal energy to unlock the next mode, vibrational mode. Okay, I have a feeling we're probably a little bit tired of this one. So probably a good time to move over to the next one. I got one last quick question coming in. I just wanted to confirm which formula we should use for our harmonic oscillator again. So if you have a harmonic oscillator, it's this guy. En is the ground state energy, which is usually provided, times n plus 1/2. Good stuff. All right, let's pop over. Shake it off. We got a new problem coming up. If you were bored before, I don't know, grab some coffee or something. Okay, let's hit Lucy. Ooh, that sounds bad. Let's hit the Lucy problem. So Lucy stands 30 centimeters before a spherical mirror holding a 5 centimeter tall candle. Looking into the mirror, she sees an image of the candle that is right side up. However, the image she sees is 7.5 centimeters tall. It's always a good idea on optics problems to visualize it if you can. Even if it's just a little rough sketch, it's always a good idea to just kind of plop something down. Hopefully it'll jog some memories. So here's Lucy. Stick figure. All right, she's 30 centimeters. I'm just going to measure everything in centimeters. So everything I'm going to mark is in centimeters. She's 30 centimeters away from a spherical mirror. So here's a spherical mirror. I'm just going to mark it with a line for now because I don't know if it's concave or convex. She's holding a 5 centimeter tall candle. 5. Let's go candle. All right, it's a 5 centimeter tall candle. She sees an image of the candle that is right side up, but the image is 7.5 centimeters tall. What is the image distance? Be careful about signs. Okay, cool. This is good. So anytime we're confronted with a mirror problem, and later when we hit lenses, there are two key equations that you want to keep in mind. Two key equations you want to keep in mind. The first one is the mirror lens equation, which is that the focal length, 1 over the focal length, is 1 over the image distance plus 1 over the object distance. Now we have some restrictions on what each of these can be. Notably, the object distance is always positive. The focal length can either be positive or negative, depending on if it's a converging or diverging optics instrument, whether it's a mirror or a lens. The image distance is negative if it's a real image and positive if it's a, sorry, positive, I almost just messed up. Positive if it's a real image, negative if it's a virtual image. So I negative means virtual. I positive means real. The difference between a real image and a virtual image is that a real image can be projected onto a screen, but a virtual image can't. A virtual image can only be seen by looking through the optical instrument. Okay, questions for a moment while we're here.
Like a real image would be on the same side as the object, right?
That's right. In this case, for a mirror, the real image is on the same side as the object. Yep. Did I
Okay,
say
but
something
like
else?
in this case, because she's looking into the mirror and the image, is that virtual then?
So, so I'll say two things. The first is that just because an image is real doesn't mean you can't see it by looking into the instrument. That's the first one. However, we'll see
Okay.
that in this case it does turn out to be a virtual image, but that's a spoiler.
Mhm,
So that's my
yeah.
spoiler. So, but okay, let's show why it has to be a virtual image. So we'll start using the things that we know. Oh, sorry, the second equation. There was two equations mentioned. Yeah, the image is right side up, which gives it away. That's correct. Okay, so the magnification is negative I over O, which is the same as the height of the image over the height of the object, measured relative to like the center line. So our candle is 5 centimeters tall. It's telling us that there's an image 7.5 centimeters tall somewhere else. Okay, so let's find the image distance. We can find the image distance by manipulating this part of our magnification equation. Notice that we have both heights, 7.5 centimeters and 5 centimeters. We also have the object distance. Lucy's 30 centimeters away from the mirror. So yeah, we can just calculate. So I'll rearrange. I is going to be negative height of the image times object over height of the object, which is negative height of the image is 7.5. Object distance is 30 centimeters. And height of the object is 5 centimeters. Oh God, what's that? It's 1.5 times 30, which is 45. I don't need calculators. I promise I'm a physicist. 45, okay. So the image distance is negative 45 centimeters. With me so far? So physically, what does that mean? Let's go back over to our chart. If we have a negative image distance, first of all, images are always measured, or both everything, honestly. But in terms of the mirror lens equation, any measurement of I or O needs to be done from the optical instrument. So the 30 here corresponds to the object distance. If we have an image distance of negative 45 centimeters, that's telling us that the image is on the opposite side of the mirror. It's on the virtual side, so to speak. It's on the non-projectable side, and it's 45 centimeters away. Boom. Notice that it's not 45 centimeters away from Lucy, right? It's 45 centimeters away from the mirror. It's 75 centimeters away from Lucy. So again, we're measuring relative to the mirror. Is the image real or virtual? Explain. So a real image has to be projectable. That is, photons have to actually travel over there. And because there's a mirror in the way, because there's a mirror in the way, this image is virtual. Photons can't actually travel through the mirror. They get reflected back, right? So for a mirror, if it's on the opposite side of the object, that's going to be a virtual image. So I'll just say virtual. And I'll type because my handwriting is horrible today. Opposite sides, side of object. And a mirror, and light can't pass through the mirror. The image can not be projected. Okay, how y'all doing? Taking a shake? Also, if you were to say the image is right side up, which gives it away, I'm also comfortable with that. Like if you were to say the image is in the same orientation, therefore, it must be a virtual image, that's okay with me too. They're equivalent. Okay, here we go, pulling through. Last three parts. Now the last three parts, this first part, we use the magnification equation. So that'll be a hint that that this one's gonna come up, right? The mirror lens equation is probably gonna come up in a minute. So I'm supposed to calculate the focal length of Lucy's mirror. That's F. So I want F. I also want the radius of curvature. This one's a little trickier. Radius of curvature, R is equal to the absolute value of 2 times F. Or sometimes we say 2F. Let's think about this. I'm down to keep it. Tell you what, let me just keep it. It's just 2F. Can you have a negative radius of curvature? Yes, you're allowed to have negative curvatures. So you're probably allowed to have negative radius of curvature. What the radius of curvature really talks about is it talks about the radius of a spherical mirror if we were to keep the whole sphere. So instead of just slicing out this little chunk that we use as the mirror, we would keep the whole mirror. It would be the sphere or the radius of a sphere of that size. Okay, but so let's calculate the focal length. So for that, we're going to need this guy, the mirror lens equation. Now, notice I'm comfortable using this now. For one, it's the only thing that has F in it that I have, right? But I'm comfortable using this now because I have both an image distance and an object distance. And now I can just calculate. So F is going to be the inverse of 1 over I plus 1 over O, which is 1 over negative 45 plus 1 over 30, inverted. And what's that number? 1 over 45. 90, all right, equals 90 centimeters. So that's F. Now I want to know, notice that this number is positive, right? Positive.
So focal length is negative, radius will be negative as well, right?
Yes, as a matter of practice, just because this is kind of like a minor point, I'll probably, if I were to ask, I would ask for the magnitude of the radius of curvature.
Oh, okay.
Yeah, but in this case, radius is positive number. So R, which is 2 times F, is 2 times 90, which is 180. Yeah, that's kind of one of the, like the R equals 2F and whether it's absolute value or not. This is one of those things that's kind of like maybe a little bit important, but it's mostly just like a mathematical convention that we use for which side of the mirror the radius bends toward, I guess, is one way of thinking of it. But thank you for the question. It's an important clarifier. Okay, so there's our focal length, 90 centimeters. There's our radius of curvature, 180 centimeters. I want to know, is it convex or concave? We don't use this language anymore. We just say converging or diverging. So for what it's worth, this is going to be a converging lens. Converging. And why is that? It's because the focal length is greater than 0. The focal length is positive. So it's a converging lens.
Wait, so is converging the same as convex?
That's right. However, it switches when you go over to lenses. And that's why we don't use
Oh,
it's because
so
it just
a converging lens would be concave, right?
Oh, so hang on. Let's hash it through. So a converging mirror gives you shelter. So if the source is over here, this is a concave lens or concave mirror. Concave mirror, which is converging. So I think I may have misspoke before. A concave mirror is a converging mirror. Concave just means that it kind of like angles itself toward the source. So the source could hide in it like a cave. A convex mirror flexes out. It flexes the light away. So if your source is on this side again, source, this would be a convex mirror, and it's diverging. It's a diverging mirror. However, like I said, we'll avoid using convex and concave at all as language, just because it's kind of like, it's kind of not that useful. Converging and diverging.
So wait, so is concave lens the same as diverging lens?
So convex lens is the same as diverging lens, or sorry, other way around. Okay, lenses. Let's talk about lenses. That's fine.
Yeah.
So lenses for a moment. Lenses do a switcheroo on us. So if I have a concave lens, a concave lens is diverging. And a convex lens like you'd see in a telescope. Actually, you see both in telescopes. But a convex lens is converging. So the reasons for this, so converging, no matter what, converging means focal length greater than 0. Converging always means the same as focal length greater than 0. Diverging always means focal length less than 0. This is really what we want you to go home with. This statement. Converging means f is greater than 0. Diverging means f is less than 0.
So is converging always f greater than 0?
That's right. Yep. Yep. In here, that's how we define it. Yep. And like I said, on examinations and stuff, we'll avoid using the language concave and convex because it's confusing, right? It's like it's converging in one scenario and diverging in another. And that just gets kind of tricky. So we'll use the language converging and diverging. It's more pedagogically sound. Okay, wrap up questions here. We can focus on it for another second. Yeah.
Adam.
Go for it.
So like even when you're talking about mirrors, like on this upcoming test, it's gonna say converging versus diverging.
That's right. We'll say converging and diverging.
Okay. All the
Is that
DL stuff
comfortable?
is like concave, convex. I don't know.
That's weird. I thought we redid it a
Just
couple of years
FYI.
ago to be only converging, diverging. That's weird. I'll go back and give it a look, but you won't be penalized either. Let's put it that way. Yeah. Yeah, let me look back at it and I'll see if I want to retrofit to include both terms. Yeah. Thanks for letting me know, Adrienne. That's weird. This is one of those things that I think of as being agreed upon a long time ago, but it's all right. Well, I'll give it a look and see. Whatever is comfortable for you. This is kind of like a quick table. This is a quick table to let you go between any of them. Sound good? Okay. Lucy now starts slowly walking backwards away from the mirror. She observes the image of the candle grows larger until suddenly it disappears. How far is Lucy from the mirror when the image of the candle that she sees in the mirror disappears? So this is a question about the mirror lens equation again. 1 over I plus 1 over O equals 1 over F. And we're looking for a point where the image suddenly disappears. So what does that mean? The image disappearing means that it goes from existing, i.e. having a value that she can see, to not having a value anymore. So we're looking for the image distance either to shrink to 0 somehow or to go out to infinity. Let's solve for image distance first and see what we get. So we get 1 over F minus 1 over O inverted. Another way of writing that is 1 over F minus 1 over object distance. Okay. So object distance always has to be a positive number. F is a positive number. So the image distance will diverge. That is, it'll go away. It'll go off into infinity when F is equal to O. Does that make sense? So these are two positive numbers. If I subtract two positive numbers that are of equal size, we would get a 1 over 0, which is kind of like infinity. It goes off to infinity. If you think about like 1 over 0.1, 1 over 0.001, 1 over 0.0001, and so on, it diverges. It goes farther and farther away. So, okay, image distance. The object distance that makes our image disappear, that makes our image go infinitely far away, is when the object distance, i.e. Lucy's distance, is equal to the focal length. Now Lucy is at the point of our object. So how far away is Lucy? Lucy is at the focal length, 90 centimeters. Let's change the color. Oh, I can't change the color. RIP. Lucy's 90 centimeters. Is that okay? And did y'all, if you had a chance to play around with a sim, that's really where the intuition for this comes from. Let me go ahead. I'll pull that up for just a moment. Hyperphysics, not hyperphysics, the other one. PhET simulation, mirror. Bruh. Back in my day, it was all in Flash. We might be in trouble. Okay, let's see. All right, that sucks. Have you all had a chance to play with that simulation though? Did it come up in DL? Okay, well, take another look at it, I say. How's that? So the idea is basically that for a converging mirror or a concave mirror, as I go from the inside of the focal length, where I'm getting that virtual image, so if I'm inside the focal length, if my source is inside the focal length, or closer than the focal length.
I just sent the link in the chat. If
Nice.
that's what you were looking for, I'm not
Thank
sure if
you.
this is the right one.
I definitely will take it. This is what I want. I'm going to make it a mirror though. Okay, great. So if I come inside the focal length, like I am in this problem, I can see this virtual image on the right. As I move further back, so as Lucy walks further back, that image grows larger and larger until eventually it's infinitely far away. Whoa, and the simulation freaks out a little bit, but these lines never cross, right? So eventually it gets infinitely far away. At that point, the image basically doesn't appear. The image distance is infinite. And that's what this problem is trying to get at. When the source is at the focal length for a, what is this? A concave mirror, the image is infinitely far away. Basically doesn't exist. Thanks for posting that, Victoria.
Yeah, no problem.
Okay, so Lucy's at the focal length. Last one, if she stands 30 centimeters farther back from the point you found in part 4, where should she look to see the image of the candle? What sort of image is this? Explain your answer fully. So this is object distance is now 120 centimeters. We know the focal length is 90 centimeters. So I can, one last time, apply my mirror lens equation. So this is going to give me an image distance, which is 1 over f minus 1 over o to the negative 1. The focal length is again just 90. The object distance is 120. That's again her distance relative to the lens. And I can draw this on a little diagram here if I want, like this. So here's the focal length of at 90 f. Lucy's now standing way over here. Okay, stick figure kind of. All right. So Lucy's standing way over here at a distance of 90 centimeters. Where does the image occur? Well, the image is going to occur, and we should have a negative 1 here. The image is going to occur at 1 over 90 minus 1 over 120 to the negative 1. What's that number? 360. Wow, that's pretty far. So the image is now a positive number. It's positive 360. A positive image distance means it's a real image. Real images for mirrors occur on the same side of the mirror as the source. So it's going to be way out here. This is a projectable image. So the photons really do actually cross in real space. They aren't blocked by the mirror on the other side. So 360 here, 360 centimeters. That's where my image lives. Nice. Okay, what sort of image is this? Explain your answer fully. This is a magnified real image. It's 3 times taller than the original. I know that because 360 divided by 120 is 3. What else? I said magnified. That's hilarious. Okay, magnified.
Wait, how did you know it was magnified?
So I knew it was magnified by the definition of magnification. So magnification is negative image distance over object distance, or the height of the image divided by the height of the object. And by that,
I see. Okay, thank you.
yeah, sure thing. And by that definition, it's also an inverted image. What sort of images?
Wait, so how did you know it was inverted?
So that is kind of another little result of the magnification equation. So the image distance is positive and the object distance is positive, 3,690. And that means the magnification is going to be a negative number.
Oh, I get it. Thanks.
Yeah, sure thing. Thanks for the questions. Okay, I think that's basically all I have for this problem. Anything else I want to mention? Okay, it's a real image because it's on the same side. I'll write this down. It's a real image because it's on the same side of the mirror as the object. In other words, the image can be projected. I got a question coming in. Sorry, for part 4, could you explain again why we needed O to equal F? Yeah, sure. So in part 4, the reason we needed O to equal F is because that was the point at which the image distance diverged. That's the point at which the image distance goes off to infinity. So that's the point where the image disappears. To use the simulation to kind of demonstrate that, we started inside the focal length, closer to the mirror than the focal length. Here's our object. And as the object moves backward, as Lucy moves closer and closer to that focal point, the image gets bigger and bigger until eventually, boom, it pops out of existence, just totally goes away. The image distance goes to infinity. That's the phenomenon that problem was trying to capture. I got another one. For part 3, how come it is concave converging and not convex converging? So for part 3, okay, cool. So for part 3, because it's a mirror, the converging lenses or the converging mirrors, i.e. the ones that can create real images, are concave. So they're angled toward the source, so to speak. They kind of like curve toward the source. They make a cave that the source could hide in. Those are the ones that make real images. So Carmen, does that answer your question? Sharon also asks, it can go to 0, right? So presumably they were talking about the image distance. So let's think. The image distance, I would say overall can't go to 0, unless maybe the object distance goes to 0. Does that work? Hang on. No, even then. So no, I don't think it's possible to get an image distance that's 0. Yeah, because this would have to go to infinity. The thing inside of the inverse would have to go to infinity. So the image distance is stuck at being a positive number. Or sorry, not necessarily a positive number, but it's stuck at being something that's not 0. Okay, I'm gonna go and stop the recording. I know I went maybe a little bit over time, so thanks for joining us if you're joining us on YouTube, and we'll see you next time.